Hello, folks, and welcome to the second lecture on attacks and pitfalls. Today will be about the so-called illegal input type of attacks. And this is probably one of the most general, one of the most common types of attacks that we have on software systems. The basic idea is that you have some software that runs, and it runs in an environment where the adversary is capable of choosing some of the inputs to that program. This could be maybe you want a web server, and maybe the web server accepts submission of some form that the user can fill in. And then if the user sitting out there is adversarial, then of course some of the inputs will be chosen by the adversary. And now the problem is that if this input is of a form, of a length, of a size, or whatever that the programmer didn't expect, and you don't verify properly whether the input is of the right form, then the software might do something unexpected. In particular, it might even, by a clever choice of the input, be made to do something that is to the adversary's advantage. This was only an explanation on a very high level, and that's for good reason, because in fact it is a very common scenario that pops up all over the place, and you'll see several examples of this. So I'll start with one type here, which is known as the buffer overflow attack. The overflow attack is probably even more general, but the buffer overflow is one of the most common ones that we see out there. The overflow stuff is something that usually arises when you attack programs that are written in C, in the programming language C. And the reason for this is that C is a language that allows you all kinds of freedom, including freedom to shoot yourself in the foot. And for instance, it's perfectly possible to write outside arrays, for instance, which is a problem in many ways. And of course, if you have a theory computer science standpoint, you might say, why even use C? Why not use a better language that will not, allow you to do stupid things like this? Which is a fair point. But the other side of that coin is that C also brings you very close to the machine you're running on, and therefore you can do things that are really, really efficient. And that means that low-level software where efficiency is very important, such as device drivers, OS kernels and stuff, is very often written in C, and it's not like there really is an alternative to that. So in reality, we will be living with C for a rather long time. And this means that we'll also have to live with the security problems that come out of using such a language. So to give you an example of what might happen, let me write down a really, really simple procedure here. That was not an F. Computer called foo, let's say. What it does is it has this pointer to a character. So something that points to an array, usually it's called in. And then it also has a local variable. That was not right. We need this one. So it has an array of characters called buff. And let's just say that it has room for 3 characters here. And it doesn't do very much this thing. What it does is simply that it uses the standard C procedure, which is called string copy, and it copies into the buffer from this input array that it got a pointer to. And then it ends. So one thing to notice here is that this is already a mistake, even if the code is very simple, because character strings in C are 0 terminated. And what that means is that if you have the area that in points to, then we can think of this as an array indexed from 0, because that's always what happens in C. And correspondingly, the buffer array also has positions 0 and 1, etc. And what the string copy does is something that it copies these values character by character, byte by byte, until it reaches a 0. At which point it will determine that that was the end of that string and now stops copying. So of course, at this point, when we get to this point in the code, we have no idea how long in is going to be. So it's not clear that there's going to be room in the buffer for the input string. If there is not, then we'll simply continue writing outside the part of the memory that was set aside for the buffer array. So that's pretty bad. And usually, if you do something like this, then probably the program will just crash. But if we look more closely at what happens inside the machine when we call such a character here, when we call such a procedure, sorry, then we can get an idea of how this can actually be exploited by an adversary. So the thing is that let's say this is the area of memory where we execute our code. At some point, when we execute one thing after the other, we'll encounter this call to foo. And after that is done, we continue somewhere else after this point in the code. So what happens when this call to that procedure is executed is actually that we have our stack in our machine. Then there's a stack frame, which is assigned to the foo procedure, which is put on top of the stack. So this is the data assigned to that particular instance of the foo procedure. And this contains a number of things. One thing it contains is the return address. So let me just write this here, return address. And what this does is to remember, after we're done with foo, where should we continue the execution of the program? So this address actually points down here, so that when we remove the stack frame here, we can actually know where we're supposed to continue the execution. But it also contains the local variables that are assigned to this procedure. So in this case, we need room for 3 bytes. So that's the array buff that's sitting right there. And so when we get to the point where we execute, that was up here, when we execute this string copy thing here, then those 3 bytes there are the bytes that will be filled with stuff from the input array that was given to the foo procedure. And now you can see that if things are placed in this way on the stack, and in fact they often are, then if we start writing here and here and here, and if the input array was too long, the next thing is that this guy here, the return address, will be overridden. And considering the fact that the adversary might be able to determine by his choice of input what is written here, that means now he decides what the return address is going to be. This, of course, is obviously a dangerous idea, in particular because if you consider, so that let's say that this was the input array that the adversary supplied, then it has a bunch of positions here that will be copied into the buffer here. But now comes the return address, and which is copied down there. And now if you're really clever, you might be able to arrange things such that this new return address actually points back into the input array that the adversary defined. And what that means is that now you'll start executing code that the adversary has written. Of course, this code is going to be running with the same privileges as the original program ran with inside the host machine. And so you can see that this is really a complete recipe for disaster. So that's something that should, of course, be avoided. And the problem, again, is we didn't check here. We just copied directly into the buffer without checking whether we had room enough for the data. This is a typical example of failing to verify the correct form of the input. So there are all kinds of ingenuity people apply in being able to exploit such bugs. And the main take-home message here is that basically one should think that every bug is exploitable. Whatever mistake you make, probably someone somewhere is going to be able to find some way to exploit what you did. It's something that people generally don't quite believe when you tell them. But I think it's important to understand that this really is the case much more often than you think. Let me give you one example of this. So let's say that we have another little example of some code. Let's say again, we had this local variable buff, now in a different program, let's say, and the programmer realizes that because strings are 0 terminated, if you just fill data into this buffer array, then maybe this terminating 0 will not be there. That can of course be a problem. So what he decides to do is to make sure that there is a 0 at least somewhere at the end by manually placing a 0 at the end. So what he does is the following. He calls size of, which is a standard C procedure, which returns the size of a given variable, right? So if we had the buff from the previous example, then size of buff would be 3, would return 3. And then he assigns a 0 here, thinking that now he put a 0 at the end of the array, and so it's probably terminated as a C character string. If you're familiar with C, you probably have already seen the error here. And the problem, of course, is that arrays in C index from 0 always. So that means that in fact, the last element in the array that's actually assigned to that array is going to be a position size above -1 and not this one. So this guy here is actually outside of the array. So now you've written the 0 where it shouldn't be. And that's of course a bug. So what do you think? Is this thing going to be exploitable? So, I mean, on the face of it, it might not seem that way, right? Because it's only 1 byte. Come on. And it's always assigned to 0. The adversary cannot even choose what the value is going to be. But nevertheless, we can actually see, if we look more closely, that sometimes it actually could be a serious problem. And again, the problem has to do with how stack frames, what they contain and how they behave. So let's draw a stack frame once again. So here's again the stack frame for the current procedure in which this problematic line of code is located. And one thing I have to tell you here is that, which I kind of suppressed before, a detail is that when you remove the stack frame, so when you return from the current procedure, you have to move the top of the stack. So the top of the stack is right here now, but then when the stack frame goes away, this stack pointer should be moved and now be placed down here instead. So the way you do this is actually by saying, okay, and I should say, where's that pointer? Well, there is a stack pointer standard register on your CPU that always points to the top of the stack. And so what happens is that when this procedure started, we pushed on stack the old value of the stack pointer. This is placed somewhere in the stack frame. And when the procedure is done, we take this value and put it into the register on the CPU. And so automatically now the stack pointer points back to where it was before. So this is fine and good. But now let's assume that the oops, I accidentally erased something here. That was not the idea. So let's say that the array buff is stored here right next to the old stack, the value of the old stack pointer. And this could actually mean that now this byte here, 0 here, is going to be show up as a 0 in the value of the old stack pointer. So this is now changed. So 1 byte of this value of the old stack pointer has been changed to a 0. And what are the consequences of this now? Well, the point is now that can I erase something? So if you look at what is now going to happen when we remove the stack frame here, well, then we take this wrong value of the old stack pointer and put this to the stack pointer. So now the consequence of this, of course, is going to be that now we point somewhere else. If this was a least significant byte of this thing, points a little bit displaced from where we should be. So one consequence of this now is that we remember what is also in the stack frame is the return address. Let's just say that the just for an example, let's say that the old stack pointer is here, and then the return address is at the bottom of the stack frame. This doesn't have to be the case in real life, but just as an example. So if this is the size of the new stack frame and the computer thinks the stack pointer is there, which of course it shouldn't be, then it thinks that the return address is actually down here. But in fact, of course, that's not really the case, because you should be pointing up here instead, but you're not. So the return address is just somewhere else. So now when you use this thing as your next return address, you'll be using the wrong value. And it could be that data area where this purported return address is actually something that's controlled by the adversary. Because again, we have some local variables here, maybe that's input that the adversary can determine. So in this indirect way, we actually end up maybe having a return address that the adversary can decide as a result of this one byte here becoming a 0 instead of what it should have been. That's maybe hopefully an example that says that even if a bug looks like it cannot possibly be exploited, it could well be anyway. And the other take-home message here is that if a pointer is assigned the wrong value, which is what we have here, then even if the adversary cannot choose the new value the new and wrong value that's being assigned, then it might still be a problem, because the adversary might be able to control the place where this new value points to. And then you are just as much in trouble as you were before. Okay, so so much for this. I hope you guys will have learned that bugs should be considered exploitable always, and you should always verify your input. It's something that people often do at the end. You know, first you put together something that just works without worrying too much about checking the inputs. And then you might or might not get around to actually doing that verification, but it's important to actually do this. And of course, in real life, when you guys go out and get jobs in software development companies, it might not be so easy to always get this done. I mean, imagine that you put together some prototype for something, and then the boss comes around and says, "Oh, that's fantastic! It already works. We can ship this next week." Then, if you're the new junior programmer, it's not clear that you feel you're in a position to say, no, we cannot. We have to verify the inputs. We have to do some more development before this is safe. But yeah, it might be that you really have to put your foot down there. Okay, so let me give you another example of this illegal input type of attack. Now on a completely different level, more on the application level, I would say. Namely something that's known as cross-site site scripting. This is something that is often a problem when websites do not verify the inputs properly. So let's look at the actors in this little show here. So on one side we have this website called naive.com. So what these guys do is that they run a search engine, let's say. And then when we have, so let's say we have our user here who sits with his computer. Here's John Doe with his computer. And then what he can do is he can look up the naive.com website, and they have the search engine. He can search for something. And when he presses the go button on the search, then a request will be sent to this website here, which contains basically the information that this guy wanted to search for some string, let's say str, some string str. So this, of course, arrives in the form of a URL that the browser from down here is asking for, and so on, but that's not so important here. So what comes back after the search is done is basically a screen image, a new website, a new web page that is shown to the user here. And so the screen image you would see here would be probably something like you searched for and then there would be str put here because that's a string you search for, and then results, and then a whole bunch of stuff here. So this seems, benign, and why would this be a problem, and so on. Well, enter the, in some sense, villain in this game here, namely a programming language called JavaScript. So JavaScript is basically one of the main programming languages that people use when they design websites, when they implement interaction and presentation and stuff in web pages. JavaScript is a full-fledged programming language, can do whatever you want. Basically what happens is that inside the code of a web page, if this is some web page code, then there will be some characters and stuff that the browser can read. If it reaches some piece of JavaScript, then the browser will usually simply just execute this code that's there. And this results in some changes to the way things are presented and stuff like this. And this is very nice, often because you can make much nicer looking web pages and you can make them interactive and so on. So that's fine. But now consider the possibility that the string here that you're searching for is actually a JavaScript piece of code. So an executable string. Now, if naive.com does the simplest and least secure thing, then you're saying, okay, how do I form this web page down here? The result coming back. I'm simply going to take whatever was typed here and copy this indirectly into the page I send back. If you do this and no other security measures are taken, then the browser will simply say, okay, so here's a web page I have to show to the user. First it says use search for, okay, I write this on screen. Here's a piece of code, I execute this. And then some more stuff. This was not supposed to happen, of course. I mean, the user just meant to search for that string, interpreted as a character string, but now it gets misinterpreted as being something that should be executed. So you could say, well, okay, that's the user's own fault. He should know better than search for an executable string. But the problem, of course, is that it's not really the user's problem. You can see already here that, in fact, naive.com should make sure that what it gets in is interpreted as character strings and not as code. And so when you put in the search string here, you should make sure to put it in such a way that the browser will not think it should be something that should be executed. So it's really a matter of naive.com to properly validate what it gets in and act accordingly. So in this example, naive.com didn't do that. They were, well, too naive. So this is really an executable problem, an exploitable bug, this thing. So the thing is that it actually is in some cases. And the reason why this could be the case is because if you can get a string search for this executable, it's not in all cases clear at all that this string actually comes from the user's computer. Because here's the other example. So let's say we have a different website known as evil.org. So maybe the user should know better than go to such a place. But let's say they have a web page too. And they have somewhere on the web page, they have a section where you can go and search on naive.com. Plus, of course, some plausible explanation of why searching on naive.com would be a very good idea. And so there will be some field you can type some stuff in, and there will be a button you can press where it says go, and then you go and search and do the search. So the user types in stuff here and presses go, and what actually happens? Well, not exactly what the user thought was supposed to happen, because what actually goes on here is a search request again, just like before. But what evil.org has done without telling anyone else about it is that they either ignore completely the string, or at least they add something to it, so that in fact there will be some script here, some executable script that is put into the search request. And as a result of this, naive.com will treat this exactly as it treated the request that actually came from the user. So when this thing comes back, then there'll be a script sitting here, and which will be executed by the browser. And the interesting thing now is that this script actually came from evil.org. That doesn't sound so nice, right? Because now they write code that now gets executed all of a sudden on your computer. Not only that, but it's even worse because the browser that runs here on the user's computer down here will get this result page back from naive.com, and will therefore, of course, believe that if there is code in here, it must come from naive.com. Now, we know it didn't actually, but who's the browser to know? How is the browser to know? And so what that means is that this script will have access to whatever data naive.com stores on the user's computer. So that's the last piece of the puzzle. We have these so-called cookies that websites are allowed to store. And the browser will most likely have some cookie assigned to naive.com here, which, for instance, could contain username and password for our friend Joe here. The username and password he uses with naive.com. This can be a nice thing to have, because if John goes away from this web page, comes back again, then you can log in using the stored username and password without John having to type all that stuff again. And that's nice. But the problem is, of course, that whatever code comes from naive.com, the browser will say, okay, you have access to this cookie here that stores this stuff down here. And what that means is that now we determined before that, in fact, evil.org would be able to write a script that would then be executed down here as if it was coming from naive.com. So now the script can go and read John's username and password and send this off, for instance, to evil.org. And so in this way, you have stolen his private data. So not so good. And again, it's really important here to understand where the problem is. So some browsers try to stop this kind of attack by saying, I don't want to see executable script everywhere. And for instance, if you try to send off such a search request here containing executable code, then that shouldn't be there. So I'm going to stop that. So browsers try to detect this kind of attack and stop it. But it's actually very difficult to do this completely, because the only place where they know how things should be interpreted is actually here at naive.com. I mean, they make their search engine, they know their service, whatever, and they know what data should look like. So it's really their responsibility to make sure that whatever data they take in is of the right form and cannot be misinterpreted as being something else. There's too many websites in the world. Browsers cannot possibly know how data is supposed to be interpreted in every context. So it's really here that this problem should be solved. And so again, input validation is of paramount importance. So that was my examples for today of illegal input attacks. And this was lecture number 2. Lecture number 3, we'll look at more examples of other attacks.